Hello! I came across this sequence on the online encyclopedia of integer sequences, A372309, the smallest number whose prime factor concatenation, when written in base n, contains every digit between 0 and n minus 1. Let's go through an example to help illustrate the idea here. The number 34,990,090 has a prime factorization of 2 times 5 times 47 times 109 times 683. Every digit appears at least once. It has a pan-digital factorization. Now, can we find a smaller number that still uses every digit? What is the smallest? And this example is in base 10, but we could also think about this question in terms of other bases as well. Like in base 2, base 2, the smallest answer is 2 because 1 0 uses every binary digit, whoop-de-doo. But what about hexadecimal or any base in general? In this video, I'm going to walk you through how I wrote a program that finds the smallest number with a pan-digital factorization for a given base. Now, the way I like to approach a problem like this is I start by finding some solution that works, and then find various ways to improve on it. Luckily for us, we don't have to start from scratch. The OEIS page includes a Python script that works off of a brute force search. Basically, it just loops through every number, checks what digits are in its prime factorization relative to a given base, and then stops when it finds a pan-digitally factorable number. Now this is very, very slow, but it does have one super interesting optimization. It doesn't start its search at 1. Rather, it starts at n factorial, where n is our base. Why? It took me a bit to get the reasoning here, but first thing to notice is that concatenating two numbers, that's joining two numbers together, always makes a bigger number than multiplying them. 78 is bigger than 7 times 8, 102 is bigger than 10 times 2, and so on. Now 10 factorial is of course 1 times 2 times 3 and so on up to 10. If we want to turn this into a pan-digitally factorable number, we just need to rearrange the terms, then delete a couple multiplication signs, and there you go. Since replacing multiplication with concatenation just makes the number bigger, we know that a pan-digitally factorable number in base 10 will be at least 10 factorial. Same reasoning goes for other bases. Another optimization we might want to implement is skipping anything divisible by a square. If the same prime factor appears twice in a number's factorization, then we know we could just get rid of one of those copies without changing which digits are covered. Fun fact, the density of these candidate square-free numbers approaches 6 over pi squared. So that's an upper bound on how much help this optimization could provide. Ultimately though, patching up the brute force algorithm won't get us the speed we're looking for. To do that, we actually need to consider the problem from a completely new perspective, the perspective of linear algebra. Here's a quick refresher on linear algebra. The idea is that we have a bunch of variables, here are only 3, x, y, and z, and we can set up some equations that restrain what values these variables can take on. But these equations must be linear. Each term is one constant times one variable. That's it. No fancy functions, you can't multiply two variables together, nothing like that. Then we set up another linear equation for our goal. We want this to be as small as possible, but it has to be linear as well. It's kind of annoying that everything has to be a constant times a variable, but if we set up a linear algebra problem like this, it allows us to employ some well-studied, super fast algorithms to solve it. One area where linear algebra is used in the real world is coverage problems. Say I need to decide where to build cell towers so that I give coverage to a bunch of homes. Well, I can associate each tower with a variable, which will equal 1 if I decide to build the tower, and 0 if I don't. Now, a problem about which towers to build becomes a problem about what values to assign to certain variables. Next, for each house, I create a requirement that says each house needs coverage from at least one tower. For house 1 to receive coverage, at least tower A or tower B need to be built. For house 2 to receive coverage, tower A or tower C need to be built. Once we have all the requirements, we just need to add a goal. That's just adding up the constant price of each tower times whether or not we decide to build it. We want to make this value as small as possible. Now that it's set up, we just hand over these equations to the super fast linear algebra solvers, and we're done. They'll spit out a solution telling us which towers to build. Now, what does this have to do with pan-digitally factorable numbers? Well, it's a coverage problem. We're just trying to cover every digit with a prime. The equations just look a bit different. Let f10 denote the smallest pan-digitally factorable number in base 10. Our goal is finding which prime factors will be included in f10. So we take every prime number and associate it with a variable. The plan here is that our variable will equal 1 if that prime is a factor of f10 and 0 otherwise. So different combinations of 1s and 0s determine f10's prime factorization. Now we just need to determine our requirements and our goal, and our linear algebra solvers can find the value of f10 for us. The requirements are pretty straightforward. For example, in base 10, we need the digit 3 to show up at least once. So we set up an equation where a 1 goes in front of every variable whose corresponding prime has the digit 3 in it. So 3, 13, 23, 31, and so on. And a 0 in front of every other variable. If we say this whole sum needs to be at least 1, then this equation guarantees that f10 uses the digit 3 in its prime factorization. So we feed this requirement, as well as 9 others for the 9 other digits, into the linear algebra solver. Now with the requirements done, all that's left is our goal. However, here we run into a problem. We want to minimize f10, which is the product of a bunch of random primes. How in the world do we get a linear equation out of that? Well, there is an answer, and this is super cool in my opinion. What if instead of minimizing f10, we minimize the logarithm of f10? This won't actually change the behavior of anything, since minimizing the log of some value also minimizes that value as well. Next, note that f10 can be written as the prime numbers to the power of their decision variables, since those variables are either 0 or 1. So minimizing the log of f10 will minimize this product as well. We can now use the properties of logarithms to turn this into a linear equation. First, the log of two values multiplied together is the sum of their individual logs. Next, we can pull exponents inside logs out the front. And look at that. Every term is a constant times a variable. That means this is a linear goal. So we could set up both a list of requirements and a goal with relative ease. Then feed them into a linear algebra solver algorithm, which will spit back the variables telling us the prime factors of f10. Coolio. Unfortunately, there are still a couple holes we need to patch up. The first problem I encountered was a quirk of the particular linear algebra solver I was using. See, the simplex algorithm sometimes says that the cheapest way to provide full coverage to a house is building 2 halves of cell towers. Does that make sense? In the real world, sometimes it does, depends on the context. In our context, the algorithm ends up saying stuff like, the square root of 3 is basically half of the digit 3, right? Because I can make a super efficient answer by using the square root of 3 and the square root of 13, which provides a total of a whole digit 3, just like you wanted. And no, that is not a valid answer. We're looking for integers. Fortunately, there are plenty of algorithms out there that only give integer solutions, so I just changed to one of those. A bigger problem is that there are infinity primes, and no matter how efficient an algorithm is, it can't handle literally infinity variable assignments. We need to find the largest prime that could possibly be a factor of f10 before turning things over to our algorithm. This was a real headache, because the only discovered upper bound on f10 is that it's less than or equal to the smallest pan-digital prime, that is the smallest prime with all digits. This isn't super helpful. Eventually, though, I found a more useful upper bound. The first step is to calculate a pretty good guess at f10 using all primes up to some arbitrary large number. Let's call this guess g10. g10 is a pan-digitally factorable number, probably close to f10, it might even be f10. But we want to make sure there wasn't some even larger prime we missed that should have been part of our algorithm. Now, g10 could technically serve as an upper bound. Since g10 is an upper bound on f10, it's also an upper bound on f10's factors. But we can do better. Here's a variation of that factorial stuff from earlier. We start with 10 factorial, but remove multiplication signs in such a way so that k digits are concatenated. Here k equals 8. We arrange them and choose which digits are concatenated and which keep their multiplications in such a way to make the smallest value possible for a given k. This is the smallest number that has both a k-digit factor and uses every digit in some way of factorizing it. So if this value ends up being bigger than G10, we know that any k-digit number is too big to be a prime factor of G10 or F10 by extension. So we decrement k until this value ends up being smaller than G10. And then we have established a bound on how many primes we need to feed into our solver algorithm to guarantee we have actually found the true value of F10. Great! Now all we need is some fast way of finding all primes up to a given limit. Fortunately, some guy named Eratosthenes already figured out you could do that with a sieve process before computers were even a thing. Unfortunately, while this method is fast, it uses a ton of memory, and the algorithms struggle with larger bases, so our algorithm has to implement some optimizations, like using a segmented sieve. But for even larger bases, storing all primes up to a given limit itself uses too much memory. So I came up with a way to drastically reduce the number of primes we're forced to consider. Take 137 and 317, for example. These use the same digits, but 137 is smaller. So it's impossible that F10 would use 317 as a factor, and we don't even need to consider it. So every time a prime is found, a binary ID is created and stored corresponding to which digits it covers. While we're going along calculating more primes, anytime a larger prime with the same ID is found, we don't store it. It just gets thrown out. This ends up saving enough memory that much larger bases can be calculated. So that's all the holes patched up. Finally, we have our algorithm. Here it is in pseudocode. We find primes, set up requirements and a goal, then let the linear algebra solver do the rest. This here will find the smallest pan-digitally factorable number in a given base. Coolio. As advertised, this algorithm is blazingly fast. In fact, it can calculate F10 in less than a quarter of a second. And since you've made it this far, it's only fair that I finally reveal the value of F10 as 15,618,090. Also, prior to this algorithm, the smallest base 17 pan-digitally factorable number was unknown. Now, after running the algorithm overnight, I can announce for the first time ever that it is 3,867,835,835,651,310. Yay! An interesting note as well is that the vast majority of the processing time goes into proving that a solution is in fact the smallest. If we just care about getting close, we can provide very tight upper bounds very quickly. For example, in less than 15 seconds, we can find this base 36 pan-digitally factorable number, which probably isn't that far off from F36, relatively speaking. Oh, I've also used this algorithm to calculate a few new terms of its sister sequence, A372612, which has a similar definition. Instead, though, every digit except 0 should appear in the prime factorization. It only requires modifying a linear requirement from at least 1 0 to at most 0 zeros. Alrighty then. Thank you for watching. Before going, I just want to emphasize something again. I think it's so cool that we can make the linear algebra work by taking the log of the value we're looking for. The awesomeness of that maneuver really motivated me to make this video. Anyways, thanks for watching. I'll see you in the next one.